All right, so we're actually back with this question again because I feel like I did it really badly before. Like over here, like that's just an ugly mess. But I feel like I was watching the video back and I'm like, I did this. I could have done this easier. So remember, we know that this is staying still. This bar is not changing. It's rigid, and the rigid bar ABC supported by those two. And then you got the stats around here. There you got all the stats. And what's the deflection? Would be how far does this go down? And yeah, that's about it. So the trick is, if you remember from the last problem, there's like you have to check to see if it goes over the breaking point. So it says that Q goes from Q to 260 kilonewtons, but we have to check along the way to see if like that Q between here and there is going to break one of the two bars. So you know the moment about C, sum of moments about C is equal to 0, and you have Q times, was it 0.64? Yeah, 0.64 times, I'm going to just call it FE for simplicity. FE times 0.64 and FD times 2.64. So essentially what you have here is just the like you have the equation explaining this, but you've got too many variables. You have normally like two variables and you can plug in for one of them and get the other, but you have this mystery one. And because if you look at the free body diagram of this, which I haven't actually drawn yet, you have this, the bar, force down, force up, force up. You don't, if you know this force, this one's given, you don't know how it's shared between these two, because technically this one could just share it by itself. Like this one can just have all the force. So you know that there is some other ratio that describes one compared to the other. And conveniently, we actually have this beautiful triangle. It's going to be this guy. The force on this guy is going to have to be, it's going to be like this. So let's try to find an equation for like describing the distance for them, or the magnitude of force. So we know that the force in the triangle is going to look like this essentially. So when it goes, this is the thing, this is the bar. Because it's rigid, it's going to go down like this. We're going to assume that it just goes perfectly straight down because it's not actually that much. It doesn't matter. So this bar goes down to here, and this one goes down to there. So let's look at, because it's similar triangles, you just have to look at how much this one's going down, and then you can just multiply it out, because if this is twice as far, for example, that means that this one is going to be twice as far down. I'm going to take a sip of coffee. That's some good coffee. So the actual distance is the 0.64, and then this one is come on, 2.64. Actually, just 2 meters from here to here. It's 2.64 the whole way across. This trick only works right now because I'm saying the forces are equal instead of their displacements. Because normally you'd have to say the displacements are equal to each other, and you'd have to make another equation. But I know the forces are going to have to be of the same magnitude and difference because the two bars are exactly the same. Oh wait, no, it's not. I have to make sure their things are the same because they're different lengths. Ah, damn it. Okay, so I guess it's a few more steps. So that means that I'm going to divide that 0.64 over 2.64. That means that the little guy, so let's call it big beam, is going to be capital B. The big beam, how do I draw this? Like an 8. Yeah. The thing of the big beam is equal to, just put my calculator, 4.1 times the displacement of the, why is that so ugly? Times 4.1 times the displacement of little beam. Right? So that means when you go over here, you know that that the forces, I don't know what this means yet, but right now you've got this. You know this, and you know this. So then how in the world can you get this relative to the force? Oh wait, the equation for these actually just comes straight from that. So if you go this big B equals, F big B is this D, F D times, it's PL over AE. So PL 1.7 over AE, and this little b equals FE times 1, so it cancels, over AE. Fun fact, the A's will actually cancel in this because they're the same. The cross-section area is the same for both, and E is the same for both, so they cancel. So you plug it back into this equation, and then you have little b turns into just 4.1 FE is equal to, and then over here this turns into 1.7 FD. And now you can actually plug these back into this original equation because it'll make it much easier to handle, because you've now only got, you find what they are relative to each other, and then you can plug that back into this equation, so then you only get one variable, or two variables, the Q and one of these ones. So which one would be easier? I think it'd be easier to plug into, I don't know, let's rearrange this one first. 4.1 divided by 1.7. 2.4 FE is equal to FD. And then we have this, let's take the same equation. Can I select all this? No. Let's just copy, paste it right here. Look at that, it's so cool. Love that, let's make it smaller. I guess I can fit right there. Oh, no, I don't want it. Oh my god. Okay, so then we just plug this back into this equation. FD equals that. So every time we see FD, we just plug in that. So Q, why is this times? Plus negative Q. Q equals, let's leave this as just FE. You're my witness what I'm going to do in a second. FE plus, and instead of FD, we do 2.4 FE. And then it's 2.69 from here over, and then the 0.64 that we divide by 0.64. Q equals FE plus, 2.4 times, and we have to do the 2.64 over 0.64. And that turns into, oh my god, 9? All right, 9.994. I guess FE. That seems really high, but we're going to go with it. I'm going to take another sip of coffee. Hopefully, nasty fucking coffee. Hopefully all that lines up. This I'm not actually following the answers online, so we're going to just see if our numbers work. So now we all solve for Q, but we want to find Q max, because if we remember, over here, you have to check for if the T is actually legal, because if the number goes over the yield stress, then everything's broken. So we're going to see what is the maximum amount that this guy can endure. Maximum force of this term. No, not that term. Of FD. Maximum term for FD. That is unfortunate that is now hidden away somewhere. I have to simplify. That's tough. Okay. That was a mistake. It's okay. We'll work with it. So the maximum term for FD is PL over AE equals 250. No, not 250. Equals mystery. This max. P over A, because this is the max thing, is going to be 250. And the length is. Oh, we don't find maximum force. I'm confused. Hold on. We're looking for this. I have all this. I have all this. I'm looking for. I'm just looking for the max displacement. No, I'm not looking for the max displacement. I'm looking for this max. You know what? Let's try. It's 250 times L. It's 250 is the max is equal to this max. So just divided by area or multiplied by area times area, cross-sectional area, is equal to the force max. So 250 times that cross-sectional area, which is something silly, it tells you, times 37.5 times 6. And it's all multiplication, so we go divide by 1, 0, 0, 0, 0, 0, 0. And then you get, that seems really low. It's 250 times 10 to the power 6. Yeah, that's times 10 to the power 6. So it's force max for D is equal to 56,250. And if you look over here, you just have to just have to switch this around. I fucked this up when I said FE. Actually, I can just convert it. I can just convert it, because if this is 56,250, 56,250, which by the way is a lot, which is very different than this so far. So 56,250 is the max. What is the max FE? Divide by 2.4. Divide by 2.4. Boom. And then you get FE max is equal to 23,437.5 newtons. And we plug this into here. Equals, what does Q equal? 23437.5 plus 9.94 times 23437.5. Watch this be dead wrong. I just got a little bit over. Divided by 1,000, so you get kilonewtons. I got 250 Q equals 256.4 kilonewtons. Actually looks familiar. That looks familiar. Please, 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 please. Please, 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 please. Old question. Please. 250. Okay, you know what? That's actually close enough. They got 255.2. That's close enough. I'm taking that. Boom. So this is the max. And what was the max given in the question? 260. Look at that. It's a good thing we plugged that in. So we plug this. This is now the new Q. And now you can plug everything in, because you actually have the max value of Q, and you can plug it into the equation, because you have the force in each of the things. You have FE, and then you can solve for FD. Let's do it for this. Let's 256 times 10 to the power 3 is equal to no, what the fuck am I doing? So we got the value of Q. No, okay, what is the question asking again? Value of the normal stress in each link. Okay, normal stress in each link. Boom and boom. Solve for the maximum deflection of point B. Point B. So now we actually know the force in FE. We know this force. So we don't need this. I don't know why that doesn't delete. We actually know the force in E. So you have PL over AE equals that change in the delta change in length. And then you plug this in for force. You know the length from the equation was 0.64. So it's 23437 times 0.64 over cross-sectional area, which is given, times 200 times 10 to the 9. And that gives you the change in B. And then you get the answer. And I can understand that. Love it. All right, so let's bring the microphone over. Okay, so here's a cool thing that I've recently learned while doing this problem. I actually tried it by myself before, and there you go, here it is. I actually tried it by myself before, not AS, and it was actually like I got the principle right, like I did most of it right, except the problem was I didn't take something into account. And I'm going to go over what that is. So here you can actually see the steel rod ABC is attached to rigid support, so these don't actually move. So you know that the delta L for the whole beam AB is going to be equal to 0, and the temperature of 25 degrees. So that's it's unstressed at 25 degrees. So the steel is assumed to be elastoplastic, which and then it gives us the stats, and then it changes degrees by, so delta T is equal to 125 degrees Celsius. E is equal to our regular 200 gigapascals, more like a G, and our sigma yield is 250 MPa. And that little constant is 11.7 times 10 to the negative, times 10 to the negative 6 per degree Celsius. Okay, so this equation ends up being, so these two, when they're like under stress, you got the PL over AE equations, because these are going to be pushing, maybe, or pulling, you don't know. So PL over AE plus the PL over AE of this one. And then this the equation for the temperature of a beam is, if you look at our formula sheet, this constant over here fits into the equation. Where is it? How do they define it? Alpha thingy times change in temperature times L equals change in size. So essentially what you have is, and remember, PL over AE is equal to change in size, right? So if you have the change in size of the big beam, so let's do big beam, and small beam, don't have a space because I wrote this so freaking fat. These are the equations. Big beam, you have, for big beam, you've got the change in length due to the change in temperature. This looks ugly, there. Plus the change in thing due to, forces and strains and, the things, the walls holding back, right? That's the big beam. And plus the displacement of the small beam, which is essentially the same equation, which is the same equations, but I'll write them out anyway. A delta T L plus PL over AE. This is all equal to 0, because it all has to net to 0. Like this one can grow and shrink, this one has to grow and shrink, but this one has to grow or shrink by the actual same amount, or else it won't equal 0 at the end. So that's the premise of this. But here's the interesting bit that I missed. I just plugged all these numbers, went in and solved for P, and then did like work for the stress in both portions. So you get P over A and the deflection of point C. If you know how much this grows by, you know how much that moves. So essentially, you just need the answer to this equation, and it gives you everything in here except the twist. The twist is that the temperature actually goes over the yield strength, and I didn't test for that. Like this temperature, the amount of like force that goes into it is above what is allowed. So we have to actually do a test for that, and that's the part that I missed, and so I got the wrong answer. Remember, we're looking for where like the elastic limit is. Elastic limit. The yield strength, the thing. So if it goes over that, then we ignore it. So we're only going up until that point. So if it's like stretching and stretching because of the change in temperature, but then it wants to stretch all the way to here, but then it's like permanently deforming, we only count it here. I don't want it to go there. I don't know how to do that. That's like a mystery. I only want it to go up to where it can actually fully go back. So that's gonna be the trick. So to find out what T that is, you can actually factor out the T. So let's erase this and factor the T. Bring the T over and find out the T for whatever this maximum, like you want to have the maximum for the beam that's gonna break first. So plug in, find whatever force, whatever displacement this needs to break, like whatever the max, the yield, whatever. Find out whatever that max is, and then plug that in right over here, and then solve for just this. Solve for just this. We know that this one's probably the one that gets squished because this one's thicker. So if this one's not going to overpower this one, so we're going to assume that this one's the one that's stronger. The one that's going to get squished, and the one that is going to actually crack because it's going to be moving more. So we find out whatever the yield. How do I do this? Like an 8. It's like the thing yield for the small one. And what force that would be, because we know that the force throughout both of these is going to be the same. So we have to find what force would cause this one to reach its yield. So I actually am doing this wrong. I'm looking for the max force that would cause it to yield. And that force is 250 times 10 to the 6 over, man, I don't even know, times the area, times cross-sectional area, which is 300 millimeters squared. So we just plug that in. 250 times 10 to the 6 times 300 times 10 to the 300, I'm going to just do divided by 100, divided by 100, 100. Boom. So I get 75000, or 75 kilonewtons. Right? So 75 kilonewtons is the actual max force. So we can plug in this max force here, and then we find out the temperature. Like what temperature this is. This is now a test to see if delta T is over yield. And if it is over yield, then we just take this number, and that's our final answer. But if it's not over the yield, then we have to re-plug in with our delta T. We have to plug this back into the equation and solve for P because it didn't actually reach the yield. Okay, so 75 kilonewtons. We plug that into the equation. Let's look. I don't actually want to calculate all this right now. Where did they do it? They plug it in, and they get 90.812 degrees Celsius. And look at that. It is underneath. Lower. So that means that the actual yield, T yield, is delta T yield, is lower than delta T. So that means we have to take a lower one, because this one goes off into the elastic plastic region where it won't come back. So we don't want that, because we're like goalposts or something. Oh, language. So we take this one, plug it back into this equation with the new temperature, this original equation over here, plug in this delta T instead, and get an answer for what is the actual force in each of the ones. So the force inside of big, when you plug it into here, the force we get, and then What am I saying the force you get? You don't actually know the force you get. You calculate the force, and then with the force, you divide by area to get sigma. So I'm going to give sigma big one and sigma small one. And this ends up, it comes out, they clearly prep this question in advance. It comes out to 150 MPa, and this one comes out to 250 MPa. And now, obviously, you just take one of these PL over AE, plug one of these into it for either the small one or big. Let's do small because I feel like it. You plug it in, and then it gives you delta L. That's ugly as hell. Okay. Let's do it for this. You do this, and then equals delta L. And then that's the other answer. And then you finish the question, and this comes out to like 0.1 millimeters. And that was this question. Like, the only hard part about this is that you have to check for the T in the middle, because you can't just do this problem and assume that it's going to not go elastic. I didn't know, so I didn't check. How did I circle this one in? Oh, just... So, yeah, that's the important part. That's the important lesson for today. Lesson. Okay, I'm done. Okay, so in the humble opinion of a student who's actually having to do these problems, these torque ones are like a joke. All this stuff up here about this is giving me a hard time, like with the subbing in, cool ways of solving weird answers that I don't even think are right on the course outline. Like, I don't think this is right. They have this answer that I got over here. It doesn't match the one in the textbook, and I really think it doesn't match the answer I got up here with their way. But I think my way is more sound. I'm going to go talk to officers tomorrow. Anyway, this one, it's a joke. It is a joke compared to it. So this one is, so two solid shafts are connected to gears shown and made of steel, for which the allowable shearing stress is 7,000 psi. So shearing stress is tau, knowing the diameters of the two shafts respectively. So the tau max is equal to 7,000 psi. Knowing the diameters of the two shafts respectively, so I'm going to say RC for the top one is 1.6 inches. What's the diameter? 16 divided by 2 is 0.8 inches, and RF is, I can't do 125 divided by 2 in my head, 75. No. Yeah, I could not do that. 0.625 inches. So, determine the largest torque, TC max. So the max force, like the max torque that you applied here. So all you have to do is check, you plug in 7,000 here, because that'd be the max, and then check the torque in the gears to like that this one is creating on this one, and then check this. And if this is bigger than 7,000, then it's a no-go. And because this is a big one, spinning into a small one, making this one now go faster, you know that this guy is going to have a higher torque than this one, because this guy's going slower, and this guy's going to be spinning really fast, because that's how gears work. So you know, you're going to have to plug 7,000 into the bottom one, and then use the equation that's given on the formula sheet to get this guy to the top. And I'll also be writing out the formulas. So what we're going to do is assume that you're using 7,000 at the bottom. Let's check the formula sheet. So J, the moment of inertia, the second moment of inertia, sorry, is pi over 2 C to the 4, C1 to the 4 minus C2 to the 4. But because it's not hollow, we don't actually have that, so it's C to the 4. And then we have the shear stress. So you got this equation, this tau is equal to torque P over J, or in this case, radius. So if we have this, we just rearrange, except there's another equation where relationship between two individual things. So you have the T of the bottom one, TF. Sorry, I'm getting confused. It's hard enough to write it out. So we have this equation, and we use it on the bottom. So 7,000 equals TF, plug in RF over here, 0.625 over J. And you plug this in to get it, and then plug it on the bottom. And then over J. And you solve for T. Now when you have T, TF is equal to the gear ratio, so you have 4 inch and 2.5 inch. So if this is the one on the bottom that we're twisting, so the one on the bottom, or the one that you're actually twisting, goes on the top. So it's RF over R, is it B? No, RC, times torque of C. Okay, rearrange. TF RC over RF equals TC. You get TC, you plug that over into this last equation. The same one over here, this one, except the original one over here. So you have to, because you're solving for tau now, tau of C is equal to TC times 0.625 over J. And TC is in solve for over here. And then that is the whole thing. And then this is the answer. Oh, it's white now. Cool. I should do different colors. But yeah, really not that hard. This one is a joke compared to the other one. Just jot this off. All right, so another similarly very simple and straightforward question. It's all the torque ones, I'm telling you. I'm waiting for them to get hard, because eventually they're just going to start spitting out some crazy stuff I just know. But for now, it's just pretty simple. The electric motor exerts 500 Newtons. So you've got this bar. I'm just going to draw it out pretty simply. And you've got the stopper at the end, thing 1, thing 2, and the motor at the end, which is spinning it, I'm guessing, that way. This goes, I guess it's 500 Newtons in the question. Yeah, 500 Newtons. This guy is 300 Newtons. This guy is 200 Newtons. And then, so we know that this guy is actually free spinning because all of these add up to each other, so this guy doesn't actually do anything. And since it's a constant speed, so there's nothing weird going on. So torque on ABCD, which is the whole thing. Knowing that, just write that here, G equals 27 gigapascals. And that the torque exerted on pulley B, or yeah, this is shown, determine the angle of twist between A, B and C, and B and D. So here's the funny thing. Angle of twist equation, this guy, oh, that's a weird, I don't like drawing this thing, is equal to this angle twist, is equal to T, which is the torque, times the length that you're looking at, over J, which is like just this equation, times J, times this number right here, times G, just G. So really, all they have to do is, it's like A between B and C. I'll save these points, so it's just between B, this guy, and C, this guy. It gives us the distance right here. It gives us, this is constant for the whole beam, so that's 2. It gives us the torque, it's just the difference of these two. And length and J, you just solve for it. It's the diameter, which is given right here, times some fancy business. It's just pi over 2 times the diameter, or radius, to the power 4. So, like, it's really straightforward. And then you just do that again for B and D, B to D, and you take the difference between, oh, this is the part where it gets, where I actually have to think of it. You just think about the difference, this plus this, oh, it's different. Okay, for B and D, honestly, okay, this is a bit me extrapolating here, but I would break this into two parts. You take the angle from this and this, which you have now already calculated, and then just add this one. You take that angle from, I've been circling everything. Let's clear out the diagram. Then you take the angle from CD plus the angle from BC, and get your thing sum, and that's your answer. Ba-ba-boom, donezo. Anyway, this question actually got me. I've done it already, so I'm just gonna go over how I did the solution and how it is supposed to be done. So you've got M has a magnitude of 1500, so where's my mouse at? M equals 1500 Newton meters, right? And it's applied to the crank of the engine. For the position shown, determine A, the force P required to hold the engine system in equilibrium, and B, the average normal stress connecting the rod, the average normal stress in the connecting rod BC. So that's in this guy over here. I have to figure out how to turn off these straight line things. I don't like them. I don't know how to do that. In this rod right here. So the principle is, all you have to do is you take a moment about A, sum of moments about A, you know is equal to 0, right? And that is equal to, let's establish this as positive. So you have 1500, and then minus this component and this component of these two forces. Sorry, it's for this rod. This rod has two components. It has an x component. Well, that's just this way and this way, because it's probably, because this is being pushed down, it's going to be pushing against this rotation because it's static. So it's got two components. And then, if you actually think about it, this component right here is equal to P, because this guy that's being pushed down, this thing has two components over here. It has being pushed off the wall and being pushed down. And these two components over here, following this triangle over here, make these two components over here. So all you have to do is find the ratio for every pound, for every newton you put in P, how many newtons are put in here. And then that's actually just based on this triangle right here. So when you find out that ratio from this to this, you actually know the ratio over here of this and this. So then you have minus BCX, and X is this way, so that's times 0.8 times BCY times 0.6. And this guy is equal to BCX is equal to, let's call it force normal, is equal to force normal. And this guy is equal to P. And you can actually find P relative to Fn, as I said before, because it's just this triangle. So then when you find them relative to each other, you just plug them back into this equation, and then you solve for P. P required to hold the engine in equilibrium. And then you have your answer. That's it. That's the whole thing. And then at the end, B is the average normal stress in connecting rod, BC. Normal stress is just the thing is in tension or compression, and that's the stress. Hold on, what is the stress? We know how to do that. You get the stress because it's like the force over area for the cross-sectional area. Force over area. It has to give you the, there you go, see, gives you the area right here. You know the force because it's this squared plus this squared equals the answer squared. And then take that, put it there, cross-sectional area right here equals answer. So I'm not actually going to do this whole problem. I just wanted to, it messed me up before because it was confusing at the start. All right, so there is now this question. I'm actually going to do it live. Like, I don't actually have done it yet. I'm just going to try. I haven't looked at the answers. Now we're just drawing it. I'm trying to understand while I'm going and see if I can do this. I don't think this video is going to do it though. Each of the 4 vertical links connecting the 4, oh yeah, there's 4. 1, 2, 3, 4. Each of the 4 vertical links connecting 2 rigid horizontal members is made of aluminum. So they're made of aluminum. Just write aluminum here. G equals 70 gigapascals. I don't know it's, or E. I'm just going to say E. I get confused. And as a uniform rectangle cross-section of cross-sectional area is equal to 10 by 40 millimeters. For loading shown, determine the deflection. Ooh, deflection, that's disgusting. Of point E, point F, EFG. So EFG, how much each of them will go down? Okay, so for the sake of this question, obviously we're assuming that these two blue beams don't move. So what we're looking for is this guy down, this point down. So let's just redraw this. We have, does it tell us about the joints? What does it tell us? It's made of rectangle cross-section for loading shown, determine the deflection of point A of all the points. So we've got a bar that does not move. And then it is connected, or like we don't even draw the bar, that's a simplification. We can just ignore all of that. In fact, we can just say this is the bar that does not move. And it has points E, F, G. I should have done those underneath. I don't know. Fuck me. F, E. This guy. That's 24 kilonewton pulling down here. So that means if we are going to assume that the rotation point is happening right here, because that's kind of what's happening. E is going to go down, but it is also going to be, if it starts like this, it's going to start like this. So kind of relative to E, that's where things are spinning. Again, they're spinning with respect to E is how we're going to look at the question. I don't even know if that's legal, but that is how we're going to be looking at it. I'll place this. So, okay, so technically it does have to balance. So let's just look at the net forces on everything. Let's look at these. It has these two beams going upwards. Ooh, how'd that get there? It's 40 millimeters. And what's the thickness? Oh, it's 40 by 10. Yeah, we know that already. And bar here. So, sum of moments about G is 0. Wait, E might go up. No, that'd be weird. E might go up. Oh my god. Because this guy's pulling down, and this guy has to pull up, so it doesn't. This guy's pulling down, and this guy's pulling up, and this guy's pulling up. It's gonna go too fast. This guy's pushing down. Oh, I didn't think of that. Okay, so sum moments equals 0 is equal to. Like, what gives us this? There's no reason for us to have that, assuming that this bolt A is gonna break, but no. This one is 400 millimeters. This guy is 250. My drawing is not to scale. This to here is 0.25 F plus 260.65 F E. I have to go soon because I have Peter helpers. Okay, so, and we know that, yeah. So now we know FE with respect to FF. And we know the sum of moments about E is equal to 0 as well. Is equal to, oh my god, 0.4 FF. Whoop, 0.4 FF plus 0.65 times 4 times 10 to the power of 3. That's about 3 is a waste because like 2, 4, 0, 0, 0, or 10 to the 3. Like this is arguably the same amount of space. I don't know, I'm just picky. Sum of, actually we don't need to do, we could do another sum of moments for F to see this compared to that, except we don't actually need it. Let's do it anyway. Let's first solve for this. FF is equal to 0.65 times 24 times 10 to the 3 all over 0.4. This is the magnitude, so like, this is just the absolute value of these, so I'm ignoring the fact that the F has to be negative because I don't follow, I just go on feel. Don't do that. 2, 4, 10 to the power of 3 all over 0.4. Boom. So I got FF is equal to 39,000 newtons. Which is actually, I think, on point, because it has to be more than this because this guy's a force up. Sorry. This guy's a force down, this guy's a force down, this guy's a force up. This guy has to be the sum of both those guys. Does that make sense? Actually, why don't we just actually do that? 39 minus 24,000. Boop. That means F E is equal to 15,000. Save me the time of having to try replugging all that stuff. Sweet. So, and this guy's pulling down, pushing down. That guy's going up for a little direction. And I know that just because, this has to balance. And if this was like a seesaw, this guy's in the middle, these guys have to balance, both playing down, and this guy has counteracted both, so it's going up. Okay, obvious. So, what are we finding? Deflection of each point. So now we actually just plug these in to the PL over AE. And I think the fact that they're the same. I'm just thinking back to another question where it had the two beams like this, and I had like this, and there's a weight, this was the thing on the wall, there's a force down here. And how that worked. Because notice that this guy has a lot more of the force. Oh, that makes sense though. That makes sense. Okay. I'm just getting confused. Oh, we're complicating it. So if we have the beam, let's look at E first. It is two beams of aluminum. Let's just. I don't know what is this. Let's look at. Copy this. Bring it back down. Not what I wanted, but okay. Also not what I wanted. Where the hell are we? Like last time this worked so well. I could have just rewritten it at this point. Okay. Shrink it down. It's right here. Okay. So E equals. This is for aluminum. Remember that we have 2, so it's going to be actually 5 by 2. So we're going to have 2 times, I'm just going to have calculated because I just didn't before. 10 times 48 times divided by 1000000. And you get 4 times 10 to the negative 4. E was 70 times 10 to the 9. All that over. P was, we're doing, it doesn't matter, the denominator is the same for all of them. Let's say for F, we're doing no, not FF. We're doing this F equals 39 times 10 to the 3 times length of the beam, which is 0.3 meters. And there you go. I think that should be legal in terms of the way that that's gone. 39 times 10 to the negative 4 times 70 times 10 to the power of 9. So this should equal, I'm about to realize that I was stupid. No, 0.002 0.002 1 meters. So I go times 10 times 100. That is equal to 0.2 millimeters. Okay, let's see if I'm on the right track. Let's look at the answer that they got. They just didn't get an answer? Oh, CF looks right. They didn't solve all of it. They didn't do the whole thing. They didn't do point, whatever. Is this 208.93 times 10 to the negative 6 meters? I think so. Yes, it is. Because this is 208, but I rounded. Cha-ching, I did it right. Let's go. And then I'm assuming you take this number for this guy. Plug in the same thing. And bada bing, bada boom. You're done. You win. You pass. Mechanics. Holy fuck, I hate this so much. Alright, so this is the first time reading this question. The uniform rod BC, this guy is cross-sectional area A and is made of mild steel that can be assumed to be less defect with. So let's go. The stats for the rod. It's got an E and a yield. Using the block and spring system shown, it is desired to simulate the deflection, okay, of NC of the rod as P gradually is applied and removed. That is, the deflection of point CNC prime should be the same for all the values of P, denoting by U the coefficient of friction between the block. Oh my god. No, that doesn't make sense. Oh. Oh my god. So, spring and box. So this spring has to reflect the stretch of this. And then when this guy hits its yield, this guy starts sliding. Oh my gosh. Okay, this actually should be too bad. But that's like frustrating. So the Kx is the spring constant and friction is force. The force of friction is equal force of friction equals F and mu. Actually, then I just pick these both because it doesn't matter. Does it tell us the way of the box? Whereas the actual force because increase removed, as the friction point seems to be the same for all values of P. Denoting. Does it tell us mu? Okay, it doesn't tell us mu. Okay, that's cool. So we just pick force friction, which is going to be equal to the P when this is at in yield. Okay, so P equals the force. So then if this is equals, it's just that means force times the K, no, divided by K is equal to displacement. Look at that. So PL over AE equals thing. P, this is also P, let's just call this P instead of force. So E A over L is equal to K. And for this, force of friction is equal to P max. P max is equal to, apparently the area doesn't matter, it doesn't tell us the area. But it should matter, because then what if it's like 1,000 by 1,000? Like then this would be moving slower. So then this one would have to be different. I'm going to leave it in variable form because it doesn't really doesn't even give us the ultimate yield. Unless we're supposed to know this is 200 and that's 250 times 10 to the 6 times 10 to the 9. But it doesn't tell us the area. P max, force of friction, U, cancel that. Mass times mg, that's mu. This is wrong. This is illegal, right? I'm not going to do this. This is PLRE, I can't say. I have to say that they're displacement. Man, what the? What? Oh, yeah, no, this is dead wrong. P max. So it is equal to sigma yield A, cross-sectional area. Damn it. Illegal, I did that all wrong. Sigma yield area. Sigma yield area over mu sigma yield area over mu g is equal to m. Oh, look, they did it in variables too. And I got it exactly right. Oh my god, and k equals, oh my god, it's almost like I know what I'm doing. These two are the correct answers. Hallelujah.